Welcome back to ECE 320A. I do have one correction to make for this week, and that is that Thursday's office hours I'm double booked, so I'm sliding the office hours from 10:30 to start at 11. So office hours on Thursday of this week only for now will be from 11 until noon on Thursday. Homework 1 is due Thursday, so I will be in office hours tomorrow whenever those are scheduled. I don't remember. And homework 2 is due on the 12th of February prior to our exam. Exam number 1 is on the 14th of February. And however far we get section-wise in Chapter 11 with homework number 2, that's where we will draw the line for topics for exam number 1. And you should be able to look at some of the more recent exams, practice exams, to see where we are. Now, if you start looking at practice exams and you go, we haven't covered that, it may not be on this exam. It may have been on a previous semester or a previous year's exam, but hopefully I've maybe identified that in the subject line for each of those practice exams. Only look at these questions or look at these particular questions for this particular exam. Today what I want to do, and you should have had available to you 2 different lectures, notes and videos prior to today based on the last time we were together physically. One of those might have been in Unit 1, a second one might have been in Unit 2. Today's class will be the second lecture in Unit 2, and we will pick up with power factor correction from the previous video or lecture in today. And then we will start Chapter 11. We'll look at a high-level block diagram description of three-phase power. We'll talk about balanced phase sequences, and that's supposed to be an eyeball. I'm not sure my drawing, that's why I'm an engineer and not an artist, but that's an eyeball, and these phasers are spinning counterclockwise. And if you're standing there where the eyeball is and watching these phases pass you, then you will first see phase A, then B, then C. Since that's the way we normally say our ABCs, that's the positive phase sequence. So somebody might talk about a positive phase sequence. They may talk about the ABC phase sequence. Those are the same. If they talk about a negative phase sequence, then if they're standing in the same spot, they'll see the A phase first, then they'll see the C phase, and then they'll see the B phase. So that's an ACB phase sequence, and that's the negative phase sequence. And I hope that, well, these drawings are not accurate, but they will hopefully help you see that if it's a balanced phase sequence, A, B, and C basically divide 360 degrees equally. So you split 360 degrees by 3, and each one is 120 degrees apart. So if we have an A phase and I say, what's the B phase? Well, you just have to change the phase by 120 degrees. And if it's a positive phase sequence, you know it's minus 120 from whatever the A phase was. The magnitudes will be the same. And that goes for currents and voltages. That's why I haven't labeled these as I's or V's. It's just ABC or ACB. We'll then talk about the different types of interconnections at both the source and the load side of these three-phase systems. We'll talk about a Y interconnection and a delta interconnection, and I may refer to those as just the symbol Y, or I might write it out and say Y, not W-H-Y, question mark, but W-Y-E. So that's the Y phase sequence, and then there's the delta phase or delta interconnection sequence, not Y phase sequence, the Y interconnection structure. And if we're dealing with balanced three-phase systems, we can actually extract a single phase equivalent, and now we can do our conventional Chapter 10 single phase analysis, and boom, push it back and see what the different phase sequences need to be if we need the B phase or the C phase once we've analyzed the single phase equivalent. That's where we're headed. To finish up chapter 10, I want to talk about power factor correction. And this is the schematic diagram of that concept. You have some load that might be described by the real power and its reactive power. Those orthogonal combinations give you the complex power. Or it might be an impedance that you have. Here I've actually diagrammed this where Q sub L I'm assuming is positive. The reactive part of the complex power I'm assuming is positive. And most industrial loads are more inductive than they are capacitive, just because we have a lot of coiled windings in these plants that we may be driving or using. If we have a Q sub L that's positive, we may want to really reduce the reactive power that the power company sees us asking for, and we can do that by near our loads introducing a new load which is made up of capacitors, or a capacitor in this class. It might be a capacitor bank in general, but now if we apply a capacitor across that original load, we now are trying to introduce some negative Q sub L to counteract that positive Q sub L in the original load. The goal then is to introduce that capacitor, which gives us an impedance of 1 over j omega c, such that we can lower that vertical component or the reactive component of our load close, or drive it such that now the angle in that complex power triangle looks closer to 0 or is equal to 0 by the appropriate choice of C, or capacitor value, in that added impedance. That's our goal when we talk about power factor correction. In the previous lecture, we went through this idea, or we started this, by looking at a particular example. I think it's easier to talk about with an example instead of doing it generically or in general. Assume that we have two loads, load 1 and load 2, described by a particular amount of real power, a particular power factor, and a leading or lagging relationship or description on that particular load. Lagging means what is Q sub L for a lagging load? Positive or negative? For a lagging load, it's positive, it goes up, and leading, it goes down, or it's negative Q sub L. So we actually have a positive Q sub L and a negative Q sub L, and how can we combine those? That's a tough question. Just add them up, right? Algebraically, make sure that we observe the plus and minus. We will get a net load, and then we will try to figure out what we want this impedance to be that the capacitor provides. The idea, or maybe I'm getting ahead of myself, but without this capacitor in play, the current that we're asking the power company to give us may be bigger in magnitude than if we add that capacitor bank in there near our load. And we'll see that from the analysis in this example. But for now, this is our example that we're playing with. Let's work through that for the different loads, load 1 and 2. I don't have all of the component parts explicitly on the screen, but you can find those with the given information. I've essentially given you an angle and the horizontal component of this complex power triangle. So when you see that load 1, you should be saying, oh, P1 is 48 kilowatts. I have 48 going horizontally. And then I have a particular angle, and since it's lagging, I know that angle is going up. And what we will see in a minute is 0.6 for a power factor. That tells us something about the size of that angle. What's the cosine of 45 degrees? Square root of 2 over 2, or 1 over the square root of 2, or 0.707. Here we're getting some power factors on either side of that 0.7. And now we want to know which one produces a bigger angle and which one produces a smaller angle than 45 degrees. 45 degrees would give us a power factor of 0.707. So when you see a power factor and you see a 0.6, you go, oh, relative to 45 degrees, what's the angle? If we had an angle of 45 degrees, how are the real part component and the reactive component, how do they compare in value, in size? They're equal. So now we know, if we're doing the math, all the algebra, and we see a power factor of 0.6, whoa, that means that our angle might be bigger than 45. We'll work through that in just a minute. That means that the reactive component is actually going to be bigger than 48 kilowatts. With a power factor of 0.96, that's close to 1. Well, if the power factor was 1, our angle would be 0. So that's another way of thinking about what relationship exists between theta of 45 and theta of 0. Well, the angle's obviously getting bigger, or I'm sorry, smaller. The power factor is getting bigger. So a 0.96 power factor says the angle is bigger or smaller than 45 in magnitude. Smaller. And in what direction is that angle for this load 2? Since it's leading, it's negative. So now we have a negative angle that's less than 45, and it's significantly less because 0.96 is pretty close to 1. So let's use that or keep that sort of in our head or on a piece of scratch paper when we're working these problems or on the exam. And if you start punching numbers and you see something that maybe doesn't look consistent, then you can actually say that. Oh, I think I've made an error somewhere. This should be this. Let's see what we have. So here's the solution. For load 1, and I'm going to quickly scroll through this because you can do this after the fact. We had the real component of 48 kilowatts and a power factor of 0.6, and you can work these many different ways. And one way is not necessarily better than another. It's really whichever way you see come to mind quicker. But we know that P is equal to apparent power cosine of theta. We apply that, and we can actually find the apparent power because we're given 2 pieces of that 3-piece equation. We're given the power factor and the real power. We haven't been given the apparent power. We can find the apparent power, and that's now 480 divided by 6, or 80 kVA. That's the apparent power of load 1. Now we can sketch, and we can do this many different ways. We can say, oh, the Pythagorean theorem, a squared plus b squared equals c squared. Now if somebody says, what's the Pythagorean theorem? You can go, p squared plus q squared equals s squared. They're going to look at you kind of funny, but you can say, well, that's how I think of it. As real power, reactive power equals apparent power. That's the Pythagorean theorem, and now you can use that information. We know that the hypotenuse is 80, the real is 48, and now we can just draw our triangle to find what that Q is, and we know since it's lagging, it's going up. So we've calculated it that way, or you could say, you know what, I like to think in terms of angles. So now cosine of 0.6 is 53. That seems about right because we knew that 0.7 was 45. 0.6 is going to be a bigger angle. So now we have a theta of load 1 of 53. We can take the apparent power times the sine of that angle to obtain 64 kVA, kilivars, 64 kilivars. And here's the note highlighted about what I was talking about earlier. You can draw a 1, 1 square root of 2 right triangle and sort of cover your bases. You can say, oh, I now know what the cosine of 45 degrees is. That's 1 over the square root of 2, adjacent over hypotenuse. Going back to our trig, students ask me all the time, well, I'm interested in electrical and computer engineering. What should I do in high school? Really learn your algebra and trig, because you're going to use it a lot. Anyway, square root of 2 over 2, 0.707. Now that gives us sort of this Goldilocks picture. Just right, and I don't know, and P equal Q is not just right. That's kind of bad, actually, but to give you a center position to think about, you know 45 degrees, and you know what the cosine of that is, and that's when P is equal to Q. You go bigger in angle, and now Q, your reactive part, is bigger than P. That's really bad. So if you were pretending to be Goldilocks, well, this is better on the far right. So usually you say, that's too small, that's too big, this is just right. Well, maybe I shouldn't have mentioned Goldilocks, but now you understand maybe why I'm saying here's this dividing line in terms of your thought process. So if you start calculating and you say, oh, my power factor is 0.8, and your Q is bigger than your P, then you might start saying, uh-oh, I made a mistake somewhere. That's what that note is trying to get you to understand or appreciate. That you can quickly, on the back of an envelope or on a napkin, start drawing this out and convincing yourself what answer is or isn't correct or making sense. Load 2. Similar analysis. We were given similar information, except now it was leading. And so now the square root is plus or minus. We take the minus of that square root because it's leading. And now we have either way to compute it, but we have a apparent power of 25 kVA. It can't be much larger than the real power because our power factor was 0.96. It was almost 1. If we had a power factor of 1, the real part would be all there is to the complex power. The complex power would only be real. The angle here is 16.26 in magnitude. It has a negative sign because now we know it was leading. So now we have a minus 16.26, and we could have calculated Q2 using apparent power times the sine of the angle. So now Q2 is apparent power, 25K, sine of minus 16 or minus 7 kilivars. We now have S1 and S2. And sometimes it's helpful to just draw these triangles. You don't have to do it in multicolors, but I'm trying to sort of be consistent, and you now see, okay, I have the horizontal, I have the vertical, I have the complex value or hypotenuse. The total load power, without putting a compensating capacitor in play, you can look at that either geometrically or analytically or both. I tried to sketch this sort of accurately, but so you have 48 and 64 for load 1. The real part of load 2 was half of what it was for load 1, and it wasn't much of a reactive piece, but it was in the opposite direction. It was down. And now you can see that S12 for the combination of load 1 and load 2 has, let's say, a better power factor than load 1 did, because the angle is less. And in terms of numerical values for that particular S sub 1, 2 hypotenuse, it has a real part of 72K and a vertical part of 57K. And is the net loads that the source is seeing inductive or capacitive for this example? Wow, this one's easy, right? Take out a coin and flip it if you don't even know, right? You've got a 50-50 chance. And hopefully you don't have to use that coin. Here it's going up, it's positive, it's inductive, it's lagging. The current lags the voltage. If we wanted to calculate that hypotenuse, we do Pythagorean theorem again to get the hypotenuse, and it's 92 about, and the angle's 38. Now we can start using some of this information, and one thing you need to know obviously before the exam is the complex power is VI star, where that's the voltage and current of a particular element or subsystem. So in our case, if we wanted S12, that's this combination of loads 1 and 2. We know the voltage, those two loads were in parallel, so the voltage is the same across those. And the current feeding those, well, we can find its magnitude because we know that the magnitude of the left-hand side is equal to the magnitude of the right-hand side. And we know the magnitude of our voltage. We just calculated the apparent power. Now we can find the magnitude of the current that we are asking the power company to give us to support those two loads, load 1 and load 2. The current magnitude is 184 amps. That is dangerous amperage. I mean, if we were even at 0.02, it's dangerous, right, with our little hearts? Just saying. So 184, whew, you can hear that one singing. Okay, it will hum if you're, never mind. But now we have the magnitude of the current supplying those two loads. Let's just look at, since we have all of this and we can play, let's look at the magnitudes of each of those loads, load 1 and load 2. We have the same voltage. S1, we know what the apparent powers are because we found the hypotenuse of each of those complex powers. We found it to be 80K for load 1. Divide that by 500 and we have load 1 asking for a magnitude of our current of 160 amps. The magnitude of a current for load 2 is 50 amps. So you can see right there that we have to add these voltages, currents algebraically, because the last time I checked, 210 was not the same as 184. Meaning the source is giving us a magnitude of 184 amps, and each of these loads is asking for 160 and 50. Question?
So would the phases be different for I1 and I2?
So now the question was, will the phases be different for I1 and I2? Anybody want to answer that? Are they the same impedance? Each load. Is each load the same impedance? That would mean what? If they had the same impedance, then their phase would be the same for these currents because the voltage is the same across them. Right? They're in parallel. So now if we wanted to know what's the phase of the current of each one, if we knew the impedance, and we know the voltage phase, now we know the current phase. But you don't even have to know that to sort of answer your question. You can say, well, are the impedances the same? So are the complex powers having the same angle? That would mean they have the same impedance. And do the complex powers of load 1 and load 2 have the same angle? They did not, did they? So these currents are not in they don't have the same phase. So you could argue around many different ways to conclude the same information. And really all I'm doing is giving us a way of thinking about the magnitudes for now. We're not really so much interested in the phases. I think we can get enough maybe counterintuitive insight by just looking at the magnitudes. So initially you might say, well, how can you supply 184 and one load takes, what did we say, 160 and another takes 50? So they're not working in the same way, are they? They're not coordinated. They're somehow in different directions. That's the end of the aside. And now let's get into plugging this capacitor in. We now know what S12 is. S12 is the algebraic sum of S sub 1 and S sub 2. And we know that that's now real part of 48 plus 24 and a reactive part of 64 minus 7. That's S12, or 72 plus 57. Plus J57, sorry. Now we want to see what can we do with C. Too many C's floating around, but the main C is the letter C, or the capacitor. So you could sketch it this way if you wanted to. And we want to know how do I pick, can I pick Z sub C to maybe make the power factor of these two, well, it's really S12 is two things already. We've consolidated it into one. S12 and Z sub C, can we make the net reactive piece smaller than 57? I was having fun. So now I just started drawing pictures again, right? Here's another picture of the scenario. We have 72 horizontal, that's the real power. We have 57 vertical, that's the reactive power. Q sub 1, 2 is 57 and it's inductive, so it's up. The hypotenuse is 92. Now, what we want to do is find a value of C that will give us some reactive component negative so that the algebraic sum of Q1, 2 and Q sub C makes that reactive component smaller in value than Q1, 2. Is it clear what we're trying to do? Power factor correction is just trying to make that angle smaller in our overall complex power triangle. Oh, well, I guess we're finished. You wish, right? I don't. I'm just getting started. So now what do? We need to figure out what C is, right? The capacitor. Well, how do we do that? Well, first we just start writing things down. Guided, right? We try to guide our thoughts, and so you might say, well, I'm not even sure, so let me start with Z sub C. You remember the impedance of a capacitor. 1 over J omega C. So we can write that down. That's the impedance of a capacitor. And if you didn't remember that, don't tell Dr. Marcelin, okay? And I won't tell him either. Okay, you can believe whatever you want. All right, so now what's the complex power associated with a capacitor? Or you might just say, well, let me write it down this way. I know the complex power formula is VI star. I can always rely on that. So I say, okay, this is now the voltage of my capacitor as a phasor times the current through that capacitor, its complex conjugate. And now, what do I have available to me? In this case, I'm applying things in parallel, so I probably am interested in the voltage. So I may want the voltage expression for the complex power of this impedance of a capacitor. Or let me now replace the current with a voltage impedance formula. So the current, this is the generalization of Ohm's law. This isn't that hard, is it? You just have to tie all these little pieces together. And then they fit together smoothly and you can solve all these problems. So now this is V sub C over Z sub C. But we have to remember that we need the conjugate of that. And that's now V sub C conjugate over Z sub C conjugate. The conjugate of a quotient is equal to the quotient of the conjugates. You can just impress anybody you want by saying things like that, right? You just start mumbling these things and they'll go, he's an engineer. So what's the impedance of a capacitor? So we can now find the impedance of its conjugate. Just have to change the sign of the imaginary component, and there is only one component. There's no real component. We just change the sign of this. We could put that minus sign downstairs or upstairs, wherever we want. For this derivation, maybe it's cleaner to just keep it downstairs. But now we have the conjugate of our capacitor's impedance is 1 over minus j omega c. And if we plug that in now to our complex power formula, which was the magnitude of V sub c squared, that's because the complex number times its conjugate is just its magnitude squared divided by Z sub c conjugate. Well, now we have a denominator in the denominator, or we can multiply by 1 minus j omega c over minus j omega c. Those things downstairs just cancel and we're left with the expression for the complex power of a capacitor in parallel with these loads that we have is now just minus j omega c V sub c magnitude squared. What's omega? 2 pi f. Right, it's 2 pi f, right? If you don't know what omega is, you know it's 2 pi f, and in the United States, what's f when we're talking about power? 60. So now we have 2 pi times 60. And if pi is roughly 3, we know 60 times 6, I can even do that, that's 360. Pi is a little bigger than 3, so this is now 377 radians per second. Okay, so now we have omega. What's j? Square root of negative 1. That's just a direction, isn't it? So we're okay with that. V sub c bar, we know from our given information. What do we want the complex power of our capacitor to equal? Ideally, we would want it to just exactly cancel the inductive component, so we would want it to be just as long in the negative direction as it is in the positive direction. We would like Q sub c to be minus 57. So in this case, we want our complex power to be minus J 57K. But we know from what we just derived that that's equal to minus J omega C V sub C squared. And we know V sub C's magnitude. We can square that. We know omega, that's 377. The only unknown is C. We can now solve for that. And to get exact cancellation, our capacitor value is now 57K over 377 divided by 500 squared. And that ends up being 605 microfarads. And that's the value of our capacitor to cause the reactive components in this combination of load 1, load 2, and the capacitor to cancel each other out. And it may be that in a problem, I may not even have you go so far as to find C. I might just have you find a Q value to reduce, and I wouldn't even have to. Maybe somebody says, well, I don't want to go all the way to 0. Maybe I just want a Q sub C of 40K. But that's still going to draw that down. Do you see? Or I might say, I want to pick the capacitor to give me a final angle or a final power factor of so much. And now you would find the power factor, or use the power factor to find the angle. And once you know the angle, you're saying, oh, I now need to go down to that spot. So now I need my Q sub C to go down to there. So that's the length I would need my Q sub C to be. Is it clear how I could make that power factor not just 1 or an angle of 0? I could vary it to make the problem a little different. So now let's look at what that has done for us, or has that given us anything of value. Let's look at the load power with that capacitor. Or this is now after doing the power factor correction. And now it may be kind of, just believe me now, I guess. I'm saying S load. Now I'm saying the load involves load 1, load 2, and the capacitor. So that now I have S load made up of 3 parts, where 2 of the parts are buried inside S sub 1, 2. This was now 72 plus J 57, and this was minus J 57 kVA, or S load is 72 kVA. And now we might ask a follow-on question and say, what is the new current magnitude supplied by the source? Again, it helps sometimes to just write down some of the basic expressions. The complex power of our load, all of these loads together, is just the voltage of the load times the complex conjugate of the load current. But everything is in series, so this is really just the source current, and we know the magnitude of the load because all these loads were in parallel, and that was given as 500. So now we know that the source current magnitude, again, we're just using apparent power. This is now the apparent power of our load divided by the magnitude of our load voltage, which again, that's just V sub G. Or this is 72K, that's the magnitude of this complex number that only has a real component of 72, divided by 500, and this now becomes 144 amps RMS. Do you remember what it was without the capacitor? So the magnitude of our source current without the capacitor, that was 184 amps. Do you see how adding that capacitor now is requesting a lot less current from the power company? The voltage is the same, but now we've reduced really the amount of power we're requesting the power company to give us, and load 1 and load 2 did not change. We're still able to turn them around or keep them moving. We've just made the power company's job easier by adding in this capacitor. That was the motive behind, well, the motive was probably to save money, because 144 is going to be cheaper than 184 current-wise. So here, the source current with all three loads, or with the capacitor, is less than I sub G of 184 when we just had the two loads. That should just make you so excited. But that's why we play with this stuff, right? As engineers, we're trying to improve things. Here's another observation. That might be a little bit counterintuitive. The magnitude of our source current was 144 with the capacitor. What was the current magnitude associated with load number 1? Anybody remember? 160. This is now less than 160, which was the magnitude of I sub 1. This was the current magnitude for load number 1. What? Gosh. Are we doing something wrong? What's happening? Now our source is, we're just asking for 144 amps, but one of our loads is using 160. Don't tell anyone, huh? Maybe they won't charge us. But we've had to pay for that capacitor bank. What's going on? Let me try to write this down and then we can try to absorb it. The loads, load 1 and 2, that's what I'm meaning by the loads, and the capacitor. That's how we did the power factor correction, was introducing this capacitor. They are actually by each other, and they're at the load side. Well, they're actually exchanging stored energy via these reactive currents. So the loads and the capacitor are exchanging stored energy via reactive currents. Where these reactive currents circulate between the loads and the capacitor and do not have to flow across the lines. And here, when I say lines, you might just say transmission lines between the source and the loads. So the transmission lines from the source to the loads. So now that capacitor is storing energy and then it's throwing it back to the loads, and they're doing this gracefully without requiring as much current demand from the source. And they're playing by themselves over here at the load side, and the power company, they don't see it. But it's a good thing what's going on at the loads, because you've now introduced or inserted this capacitor to help you circulate these reactive currents to try to minimize that reactive component at the loads to get our power factor closer to 1. In this case, it was equal to 1. Whoops. That's a good thing. That's what we want. We want to save money, and that's what's happening. Right? Questions on chapter 10? Okay, we're moving on. Question?
So before, the current source had a complex current to it, and now it just real current.
So now the question was, before, our current source, was its phase the same as our voltage phase? Okay, so that was not clear enough. I think you're saying without the capacitor in place, right? So now, without the capacitor that we introduced for power factor correction, what could we say about the phase of our current? Is it the same angle as our voltage angle? What is that relationship? Well, we know the complex power S is VI star. And what was S? S had a real component and a reactive component, so you know that the voltage and the current are not in phase. If the voltage and current are in phase, we only have real power. And because they weren't in phase, or because we had a reactive power, then we know that the voltage and the current don't have the same phase. Okay, and now with that capacitor, now we've made the power company look at us as if we're a pure resistive load. And what's happening sort of between or at the load side is we're kind of playing back and forth locally with these reactive components, and the power company doesn't have to see that. Question?
The capacitor just eliminates that reactive component.
So the capacitor is essentially, the question or the comment was, the capacitor is now providing us with a reactive power that's just opposite to the reactive power of loads 1 and 2. Loads 1 and 2 were a net inductive reactive power, and the capacitor is purely capacitive. It's pure negative. In reality, it might introduce some real part. It may dissipate some power, but for this analysis, the C was a pure C. It gave us complete vertical direction, and now we use that to exactly cancel the inductive component or the lagging component or the positive reactive power in loads 1 and 2. Question?
So there's, after doing this example, there's a possibility that you'll throw a question at us on a test or a homework that kind of does on a capacitive load.
I'm sorry.
That focuses on a capacitive set of loads, and so instead of we would need to find the right inductor to raise that power from negative to 0.
You can talk to him after class, but apparently he's turning this on its head, isn't he? So the question, I think, is what if you gave us loads 1 and 2, actually on an exam I might give you 6 or 7 loads, and apparently they're a net capacitive, so they're negative. Now you could introduce an inductor. But in reality, in the real world, most of your power factor correction is done by introducing capacitor banks. So I can make the problem challenging enough without having to worry about, oh no, if he puts an inductor in here, now what's going to happen? But you can kind of think through that process. Does that help with your comment? I won't throw too many things at you. This battery might hurt, so I won't throw that at you. Probably miss anyway and hit somebody else. Why'd he throw something? Well, because your neighbor asked a question. Any neighbors want to ask another question? Sorry, I'm not trying to minimize questions, but just loosen the mood a little, or lighten the mood a little. Other questions on chapter 10? Then we're moving into chapter 11 because we want to really play with larger quantities of power, and that's what three-phase power allows us to do. So now that's a phi. We want three-phase power. This is chapter 11. And why are we interested? So let me just try to give you a high-level understanding of why we might be interested in three-phase power. Why is there a chapter 11 in this book? Can't we just tear it out and throw it away? No. Somebody now says, did you ever have any power in your curriculum? You can, depending on how many more questions they ask, you can either say, how should I answer that? I had Tharp. Oh, then I won't go any further. You didn't have any power. But you did have chapter 11. Okay, you've had chapter 10, which is single phase. Now you get three phase. And we'll just get the sort of the big picture right now. So here are some characteristics of three-phase power. One, it allows us to move large blocks of power. Meaning we may be using high voltages. And in order to obtain high voltages, we can actually do that if we have AC power via transformers. Just coils wrapped around some magnetic material. So now we can obtain these high voltages using transformers when the voltage is AC versus using rotating machines, which are much more involved or complex and expensive to raise and lower voltage for DC voltages. So now versus using rotating machines to raise and lower voltage for DC voltage. Or AC now says that we have less complex system for raising and lowering voltage. We can do it with a transformer. That's one reason. Another reason, maybe more significant, is dollars, economic, for using three-phase power. With three-phase power, we can actually use smaller and or lighter components than if we did everything with a single-phase system or network. So the easy way to think of that is, well, if I want the same amount of power delivered from point A to point B, then if I can do it in 3 different pieces, I can basically split it up in thirds instead of in one big chunk. And 3 smaller pieces don't require as much network component or wire to accommodate that lower current or those factors of 3 sizes currents versus the big one. We also might be interested in performance improvement. And actually with 3-phase systems, we now have steady torque supplied to our machines. Meaning we have an A phase, a B phase, and a C phase instead of just one phase. Now we have kind of a smooth A, B, and C, giving us a steady torque on these shafts of our generators or motors. So the steady torque supplied to machines means that we have less vibration and we probably don't have to service systems as much. It's more efficient. Another reason for looking at 3-phase power is if we will focus almost exclusively on our systems being balanced. So we'll look at balanced 3-phase power, And there's economic reasons for that, to have a balanced three-phase system. And what we will see is, in fact, we won't have any, if our system is balanced, we won't have any current in our neutral conductor. And if there's no current flowing in the neutral conductor, we don't have any power losses. So the power company doesn't have to bill us for those losses that are incurred from going from the source to the load. So we have no power lost in the neutral conductor. And one more item under balanced three-phase power, if we went further in the power area, some unbalanced circuits or conditions can be solved by a concept called symmetrical components. And those actually rely on a good understanding of balanced operations. There's the justification. So if you go home and put on your hat, your why hat, why? You can just go back and look at these three reasons for why are we studying chapter 11. Why? Because Tharp can give you more questions on the exam, because now we're in chapter 11. Question.
Can you have more than 3 phases of power?
You could have more than 3 phases of power. The question was, can you have? But there gets to a point where it's excessive in terms of where do you draw the line between more complexity? Now we have a 6-phase system versus a 3-phase. It's convention pretty much to focus on 3-phase. So now let's look at a block diagram of a 3-phase system. And when I say a block diagram, it is a very crude block diagram. There's a block representing our 3-phase source. So now we have possibly 3 lines coming out of that source, depending on how it's interconnected, and that now goes through transformers and transmission lines. Then, so on one side we might have transformers, on the other side we might have transformers, so we may really crank up the voltage, ship it down the transmission lines, and then coming into your house, it's not very high, is it, voltage-wise? Well, it's stepped down again with transformers as it gets closer and closer to the destination or the loads. And here, on the right-hand side, are our 3-phase loads. That's my block diagram of a 3-phase system. And we are going to what? Not really worry about this, so we'll just WLOG that. And you guys text all the time, so I know you know what WLOG is. What? You're engineers, so you know what WLOG is, right? Oh, maybe you're mathematicians. Without loss of generality. So now when you're texting tonight, you can just say WLOG. Sure, Mom. So now you have, without loss of generality, which means we can omit the transformer part of this and just deal with high voltages. It doesn't really change much in what we need to learn in this class. So the transformers can be omitted in our discussion. That's WLOG. Okay, so now let's look at some balanced three-phase voltages. Here's V sub A, and this is a phasor, so it's a bar. That was supposed to be a bar. We have a V sub B, and you can make these more accurate if you want, but I'm going to be just quick, and so they may not be quite as accurate as they need to be. And then this is the C voltage, the C phase voltage, where all of these are now, since it's balanced, all of these are 120 degrees apart. And as I said before, if you were sitting here and eyeballing this, let me spend a couple 10 minutes trying to draw an eye. But now you have an eyeball, and these phasors are actually rotating in a counterclockwise rotation. And as you're sitting there, boy, that's bloodshot or something, isn't it? Let's do that. Well, I was going to say let's make that better, but that's going to be impossible. So let me redraw it.
You know, you could just do a little dot in the middle.
Oh, I have to get fancy. So there's an eye. Now it's teared up, I guess, or something coming out of it. But you get the idea. Now as that's spinning around, we could say that the A phase is now some magnitude, V sub M, at an angle of 0 degrees. So that V sub A was supposed to be flat at 0 degrees. And this is now called the A phase voltage. Did I see a hand raised? Yes.
The arrows of the angles have nothing to do with the red arrow. You were just indicating that they were 120 degrees apart.
Yes, so thank you. I guess I'm confusing you, aren't I? These blue lines are not indicating a direction. That they're just indicating a angular separation between the A phase, the B phase, and the C phase. So now does that help, making them two-headed arrows? So now I'm not indicating direction of rotation of those 120s, the blues. These are now, if you say 60 hertz, this is spinning around now at 377 radians per second, and it's counterclockwise. So you're seeing the A, or it's doing 60 times a second. You're seeing A 60 times in a second. You're seeing B 60 times a second. So A and B and C, boy, they're banging right by, aren't they? A lot quicker than that was with my snapping. So you're seeing now ABC. If that's the A phase, now you know what the B phase is. It has, if it's balanced, it has the same magnitude, and what's its angle? It's now minus 120 degrees, and this is now the B phase voltage. And finally, the C phase has the same magnitude. These are balanced. And what's its angle? Minus 240 plus 120. It's 120 away from B and A. Typically, we try to keep these angles between plus and minus 180, so we might say that this one now is plus 120 degrees, and this is now the C phase. And in fact, this is the positive phase sequence. Or the ABC phase sequence. So if somebody says I have a positive phase sequence, now you say, oh, let's see, and somewhere I learned my ABCs. It's ABC, that's the positive. So now you say ABC, and that's the positive phase sequence. And now you know what those look like relative to each other. And if your A phase was actually at 30 degrees, then the B phase is 120 away from that. So it's now pointed straight down at minus 90. Question?
How come it's ABC if, like, we look at the rotations going counterclockwise, wouldn't it make more sense to be like ACB?
Am I not seeing something here? Let's see. So the question was, why is it ABC? I'm saying that we're standing there where the eyeball is, and now this is spinning counterclockwise, and what's going to slap you in the eye in terms of these phasers? You're going to see A first, then B, and then C. Does that help? So now just remember that these vectors are rotating counterclockwise. So now if you're standing where that eyeball is, boom, there's A, B, and then C. Does that make sense? Correct. The observer's standing still until he gets slapped, but then those phasers are hitting him or her. It's better if it's a he there. So the guy is getting slapped, A, B, and C, right? 60 times a second. So you're getting hit 180 times, aren't you? Because you've got an ABC 60 times. So if my jaw's a little bit bruised Thursday, you'll know why. I was looking at those phasers and seeing ABC. So if that's the case, what's the negative phase sequence look like? So now you can draw this tonight, right, can't you? Yes, you can go home and talk about W log and what's W log again? Without loss of generality. So now we have a negative phase sequence. And this is the ACB phase sequence.
Are the vectors still spinning in the same direction?
And what is really happening here? Now we have a here, V sub A. Here's V sub C. And here is V sub B. And they are exactly spinning in the same direction. They're still going counterclockwise. So now it's ACB. So what did I say here? ACB phase sequence. This is the negative phase sequence. So if I now gave you a V sub A, ooh, I don't want it in red. If I now said V sub A is V sub M at 0 degrees, what's V sub B? And now I'm not writing them in the right order in terms of the way your eyeball's seeing them, but you can simply write down your phasers. If somebody says, oh, I have a negative phase sequence, I might just write this picture down on my piece of paper, on my napkin, on the back of an envelope, wherever. Oh, it's a negative phase sequence, it's ACB. And now maybe in fact V sub A is sitting up here at 30 degrees. Well, now you know that C is 120 behind that. And B is 120 behind C. It's ACB, ACB. Does that help? So there's our phase sequences, positive and negative. We'll look at the way we can interconnect all of these in a Y and delta, and we can do the source and the loads in Ys or deltas. All sorts of combinations to have fun with next time we are together. See you then.